Hi, kids. Time to start putting some of these thoughts about partial derivatives and what we're doing into context a little bit. So with partial derivatives, we've been taking apart, right, the slopes of these 3D surfaces and talking about the rate of change in only the x direction where we hold a y constant, or rate of change as we hold x constant, right? So you're thinking of your surface, right, is your function. It takes some point, your domain is x comma y, takes some point from the domain plane here, operates on it, and pops it up into 3D. So when we take a think of a vertical plane coming down through this surface, holding y constant, right, just takes this trace of the curve. The blue curve is the trace of a vertical plane slicing down through this figure onto the xy plane. And then that reduces our two-dimensional derivative problem to one-dimensional because we're holding y constant. But holding y constant means that the slope of this line, if I project it down onto the xy plane, this vector shows me the direction of that derivative. If I do the same thing in the y, if I slice a plane down vertically through the xy plane, get the blue curve, right? No matter where I move my plane that I'm slicing through, as long as I hold x constant, I project my tangent down onto the xy plane, I'm going to get a vector, right? I'm going to get a vector that shows the direction of the derivative. That's called a directional derivative, a derivative with direction. Notice, though, that when I'm holding y constant, my directional derivative that's projected down there onto the xy plane is parallel to the x-axis. And when I'm holding y constant, my directional derivative is parallel to the y-axis. Well, what if I don't want to be parallel to either? The directional derivative can find me the instantaneous rate of change in any direction, and I need you to picture the directional derivative as a vector that lives in the xy plane and tells you it is a vector with the components, the horizontal and vertical components of the rate of change. Now I need you to think about where the rates of change come from, right? Where in Calc 1 how did we come up with the derivative? Right? The derivative was we took a point here, we called it Q. Here's our original point. We drew secant lines. We wrote an expression for the slope of the secant line. And then we took the limit, didn't we? Now remember, I'm projecting down onto the xy plane. So when I project down onto the xy plane, I have vector p prime q prime. But vector p prime q prime is parallel to what I'm calling the directional derivative, isn't it? So maybe, because it depends upon where I put this point. As I shrink this point closer to 0, right? So that the change in f is approaching 0, right? If I call the change in f h, just like we called the change in x h, right? So as or I shouldn't say change in, right, my f x y's maybe. Anyway, these two are parallel. Well, what does it mean to be parallel? For vectors to be parallel, it just means there is a scalar multiplication of vector p prime q prime to get to this vector that I want. the purple vector, the directional derivative vector. So how does that help? Here's the formal definition of the rate of change derivative in the direction of that purple. Now, here's something I didn't really say yet. We are expecting u to be a unit vector. It is called the directional derivative, and this is its notation. And the definition of that derivative is a limit. Here is f of x plus a plus h. So what is this, right? This is just like y2. Think of that projection down there on the, right, down here. Remember, this point is now x naught, since I projected down, x naught, y naught, 0. And q is xy 0 because I'm in the xy plane. So moving, what is the change here? The change is starting at x sub 0 or x naught. You're going to move this distance a, but don't forget, because it's parallel, I need to multiply by that small change, right? Multiply by the small change in x, small change in y. So that's where this notation comes from here. Minus the original x and y all over as that h goes to 0. Now, just like in Calc 1, we ditch that limit notation pretty quickly. And we have the partial x, right? The partial x is the derivative in the x direction multiplied by that, our unit vector, plus the derivative, the rate of change of y, so the vertical change multiplied by the vector, the vertical component of the vector. And of course, I can extend this to 3 dimensions as well. Let me take you to a graph of this. So here's this pink surface is in 3D, right? Up there in the, up here in Z land. Here is the tangent line drawn in red and the curve here in black, right? So do you see the 2 points? The point there, Q, and then projected down onto the XY plane. And you can see the directional derivative in that vector is in orange. This orange directional derivative is the projection here of the tangent line down onto the XY plane and then scaled, right? Made it a unit. So let's do an example. I'm going to use the same, this is the same picture. So this shape here, this is the shape of this kind of greeny yellow surface. This point is 1/2, negative 1/2, but I cannot do the problem yet. find the directional derivative at a point for a surface, but I need to tell you what direction I want. Or of course I could write that as I plus j, right? So this is where sometimes the notation gets confusing because they wrote u. You have to make sure that u is a unit vector. Is it? No. Its length is root 2. So how do I get my unit vector? 2 bars, 1 bar. Right? Then I'm just going to use my formula. My formula is partial x, which is negative 2x. My formula needs partial y, which is negative 2y. And then here's the x and y that I'm given. So the partial x at this point that I care about. What is the rate of change with respect to x? At that point is negative 2 times a half. So that's negative 1. And what is the partial of y? Negative 2 times negative a half. So that's positive 1. Now, what is my directional derivative? Negative 1 times a. And, because that's in the x direction, how about in the y? Times b. And what do you get? Shockers of all shocks. I get 0. So what does this say? What this is saying is that if you're at this point on the surface, right, you are, right, if you move a unit away, right, you are constant. You are, your rate of change is constant. You are not going to go anywhere. Not going to change elevation, I should say. Let's try another one. This time let's do 3D. So if you want to pause the video and see if you get the same thing as I get, once again, I need to tell you what direction I want, right? So I've left off that both times because I want to make sure that you look for it. If they're asking you for a directional derivative, they have to give you a surface. They don't have to give you a point, but we usually are interested for at a point. So they give you a point, they give you a surface, and they need to give you a direction. You need to decide if u is a unit vector. It is not, right? It's a length of 3. So I need my partial x. And what would my partial x be this time? And then there's no constant. Partial y. And partial z. Sorry, I dropped a negative there. Evaluate that at our x, y, and z. 2 times 1 times negative 2. 1 squared minus 0 squared. Negative 3 times negative 2. Oh, I can't read my writing. What does that say? Negative 3 y z squared, right? Plus 1. Well, I'm going to put 0 in there. A z is 0 is going to wipe that out, so I'm just going to get a 1. So now my directional derivative of this function at the point 1, negative 2, 0 is negative 4 times what? Where's my a? Where's my unit vector? Ah, my unit vector right? So it's 4 times, negative 4 times 2/3, and 1 times 1/3, and 1 times negative 2/3. That's what I have, negative 2 and 1. So this is negative 3, I think, if I've done my math right. Now remember, this is a directional derivative. It's still a slope. Think of it kind of like, sort of like over 1. What this means is that every unit you travel in this direction, f from, of course, this point, in the direction of vector u, f goes down by 3 units, right? You're going down a surface. Directional derivative. So here's where kind of sort of this stuff, one of the applications of this, I'm hiking along a mountain, and right, I have lots of different elevations, obviously. I have a horizontal, a vertical, and a height position. If I want to walk in this direction, this is my directional derivative I want to go. If we choose to think about the horizontal distance traveled, the directional derivative is the hiker's change in height in terms of the horizontal distance traveled. Here's another visual, right? So here's like a mountain range, right? Or some mountains here, and here is the contour map, right? Looking from above. You see this point here? As I move this point, right, can you see what's happening? The slope of the dark green, the directional derivative is the slope of that dark green vector. And it's showing me where I'm going, which direction I'm going as I move this point. If I take this point anywhere, right, moving along, right, the directional derivative is a slope. But you see it projected down here onto the XY plane. That's this image here, right? What is the slope right? I'm going up, 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 up. Right, anywhere. Where am I pointing as I'm going horizontal? Let's do another example. This time I gave you the full example. Find the directional derivative. This time, no point, right? I'm just giving you, I want the directional derivative at any x, y, z. I've given you my surface, and I've given you the direction. This time I called it v, which should be a clue that I definitely don't have a unit vector yet, right? So that's the first thing I looked at. So I said my unit vector, and this is my way of avoiding the whole u over the magnitude of u. I found my partial derivatives, and then I just plugged and chugged into my formula. Now I want you to look at my color coding there. The reason I wanted to do this one not at a specific point is I wanted you to look at how I might rewrite this expression. So in gray there are the partial derivatives, and then in that reddish color is the unit vector, right? The components of the unit vector. So I want you to, now yeah, I went through that problem very fast, but it's because I really just wanted to get to this end part. So if you need to pause and write that down, because I want you to notice how I could have rewritten that. There it is again. And remember, all the XYZ stuff are your partial derivatives. Look at what I did. I kind of undid a dot product, didn't I? So isn't it true those are all the partial derivatives? If I create a vector of the partial derivatives and dot it with the vector, the unit vector, isn't that the partial derivative? Isn't that the, directional derivative, just in a different form? But that's kind of nice. The directional derivative is a dot product, and it is a dot product of the vectors made of the derivatives times that unit vector. Right? The dot product is a sum of products. Partial derivative times A, partial derivative times B, partial derivative times C. OMG. Mind-blowing. The directional derivative is the dot product. And remember, the directional derivative is a slope, right? It's a value. So the directional derivative is a dot product. Now, when I leave the x's and y's out of it, I'm not going to get a value, but I just have to plug the x, y's, and z's in it to get a value. But remember, a dot product is a value, right? The dot product between the partial derivatives and the unit vectors gives us the direction of change. Whoa. Hey, look at that vector. That's a kind of cool, right? A vector made up out of partial derivatives. I feel like that. I don't want to keep saying that. A vector made up of the partial derivatives. I feel like I should have a different name for the vector made up of the partial derivatives. There you go. There's your name. It is called the gradient of my surface. And this notation, upside down triangle, who knows why, is the notation for the gradient of f. The gradient of f is a vector, right? The directional derivative is a value. It's a slope. It really is the result of a dot product. The gradient is a vector. Right? It is a vector made up of the partial derivatives. The gradient vector. So I can think of two different ways of coming up with the directional. Oh, I forgot my little arrow there. The directional derivative. I can think about the directional derivative, right, as it's horizontal, vertical, and height, kind of, right, x, y, z. But I can also think of it as a dot product of the gradient vector times the unit vector of the direction I want to travel. This picture is in your book, I think, or something similar to it. Again, goes to the idea of where that, right, the unit vector living down here in the xy plane, right, the directional derivative. It is a projection of your tangent line. Here's a picture of the plane you can see coming down, right? Here's the vertical plane coming down through the surface onto the xy plane. Here is the curve C. The curve C created, it's the trace. Here's my tangent line. Here's the point P that the surface and the tangent line share. Here's the point Q that is on the curve and that plane. And where I write the rise over run, that's all this is, rise over run, and taking a slope formula of a secant and turning it into taking a limit, getting the tangents. Kind of crazy. Now let's think about that hiker on the mountain again. What if she wants to know the fastest? So she just doesn't want to know her, right, the rate of the rate of change, the direction of the rate of change, or she wants to know. So I made my mountain not as a little bit more mathy, put it on an XY plane sort of, instead of that first picture I had of the hiker. But let's imagine that this is, right, mountains, and I'm hiking along, right? I'm got it at a high point of elevation, and I'm coming around, I got lower, right? Can go down here to even lower. I'm going to put some level surfaces on it, right? So I'm going to cut through my mountain at a height of 2. So Z is equal to 2, constantly 2 here, 1.6 here, 1.2 here, right? That's the idea of slicing through that curve and making our level surfaces. And then remember, we talked about making a contour map, right? So if I just project all of those level surfaces down onto the XY plane, this is what it looks like. If I bring the contour map up into the XY plane, how we're used to looking at it, kind of looks like that. So let's say I'm standing at an elevation of 2. And I want to know, which direction should I go to maximize my elevation, the change in height? So let's say, oh, that's a terrible spot. Let's say really I'm over here. Let's say I'm somewhere here. Oh no, think the level curve of height is about there. If I project that down here onto my contour map, I can't tell. Am I closer over here or around the other side? Let's pretend I'm here on my contour map. I'm totally missed with that. I don't know what the heck is happening with that. I probably moved my picture at some point, but I mean it to be here. So I want you to think about that if I make my function that gives me my height constantly equal to 2, and I slice through here, I'm making some, right? There is some trace that corresponds down here on the contour map. But I'm standing here. Well, that curve up in 3D space, didn't we learned this before. How do I write the equation of a curve in space? Right? It's the horizontal position with respect to time in the I direction and the vertical for the J direction, right? So if I want to think about how I'm walking along this surface, well, and how my elevation changes with respect to time, isn't that the chain rule? I want my elevation, and I want to say, how can I move to keep my height constantly 2? Right? If I'm standing on the contour curve z equals 2, how do I not change my height? I stay on the contour curve. I stay on this same, right? As long as I walk a path where I'm on that same contour curve, I won't change my elevation. So this is the chain rule, right? I've done a composition of the function that gives me height. I want to stay constantly at a level of 2, but this is my horizontal and vertical change with respect to time. Notice the color change there. Okay, what have I done here? I'm taking the derivative of both sides of this equation. I'm taking the derivative of a composition. Taking the derivative of a composition means I need the chain rule. Taking the derivative of the right side 2 gives me 0. So I'm taking partial f, the change in elevation with respect to my x position, times my x position, the rate of change of my x position with respect to time, and doing the same thing in the vertical. And remember, we see the chain be the chain. Now, that's okay, I guess, but I want to use that same thought process with you that we did before. Look at this expression right here. It is a sum of products. A sum of products. A sum of products equal to 0. Hey, what have we been doing in gradient land, right? In 3D land, where we have a sum of products. Undo the dot product. Undo the dot product. So take a moment and believe that those two things are the same. These two lines are the same. Right? If I dot these two vectors, don't I end up with this sum of products? And again, equal to 0 because I took the derivative of both sides. Now, look at this. What is this? Hello? That is a vector of partial derivatives. What G word did we give that? What is this? This is the regular rate of change of x with respect to t, rate of change of y with respect to t. Hey, where do I have x and y? Oh, I called that r. So what must this be? Oh, snap. Oh, snap. the gradient vector dotted with the, what is this? I know what the purple is. R of t is my level curve. Oh, there's this one on this slide. I put my dots in the right place. Oh, no, it's supposed to be down here. Oh, whatever, you get it. Where was I? Oh, at this point, right, here's my curve. That's R of t. R prime of t is the slope of the tangent vector. So what does this say? If the gradient of f dotted with the tangent vector is equal to 0, what does that tell you about the relationship of the gradient vector and the tangent vector? If your dot product is 0, you must be perpendicular. The gradient vector is always perpendicular to the tangent vector. Oh my goodness. Why do I care about that? Well, firstly, let me show you this again. This is the same image that we had before, or the same applet, but with the second page, where I'm going to add the gradient vector to it. So if I have the gradient vector is perpendicular to the level curve, right, where you've sliced through f of fxy, or I just did f of xx, f of xy, made it equal to a constant, took the derivative of both sides, so the derivative of this constant was always 0. Notice now that there are 2 arrows along here. Right? And do you see the perpendicularness? Look at the shadow down there. So the gradient gosh darn it. I don't know. It goes away. I didn't want it to go away. The gradient vector is always perpendicular to that tangent vector. Why do I care about that? It's going to help me think about a new way to think about the tangent plane. Right? Your gradient vector is always going to tell you, should go back here, I'm sorry. The fastest way to climb the mountain, your gradient, and this should make sense. If your tangent vector, if you're going in the same direction as your tangent vector, right? What does it mean when your dot product is, for instance, equal to 1? It means you're the most parallel. If your gradient vector, right? If you're staying along your curve, you're not going to go, your rate of change isn't going to go anywhere. But your gradient vector will point in the direction of, right? This is going tangent. Your gradient vector will say, hello, if you want your fastest way to climb the mountain, go straight up, right? No matter where you are, no matter where your dot is. The tangent plane then has this equation, right? A new way to think about writing the equation of a tangent plane. If the gradient vector is always perpendicular to the tangent vector, but the tangent vector lies in the tangent plane, I now have a way of thinking about writing the equation of the tangent plane, right? With partial derivatives. The partial derivative at the point, partial y, because this is the gradient of f, which is always perpendicular to the tangent plane. And isn't that all you need to do to write the equation of a plane? You need a vector perpendicular to the plane. Bam, there's your gradient. So if I ask you to find the tangent plane and the normal line to this sphere, the first thing I need to do is just find the gradient vector, which is the partials, right? The vector of the partials. And this was a nice one, 2x, 2y, 2z. I plugged in 1, negative 2, 5. Wrote the equation of the tangent plane using the normal, right, vector. So that's my slopes, if you will. The point equal to 0. And then if asked, I can expand and do all that kind of stuff and make it look nice. I could even go further and divide everybody by 2 there, couldn't I? So what about this normal line? Do you remember how to write the equation of a line? What I mean by normal line is using your gradient values, right? The normal line is perpendicular to the tangent plane. The direction of the normal line is your gradient. So point, slope. So I gave you the normal line. For some reason, normal lines, when asked in this context, the symmetric equation of the normal line is given more often. I don't know why. I won't, if on an assessment, I can ask you, only if I mandate a form, do you have to give me a particular form. So I know that was a lot of information, and it was a lot of me desperately trying to show you how I would be moving along a mountain and hiking and trying to pull up applets to try to get you to see what's going on here. But your big ideas to come out of here, the things that you need, can you find the directional derivative of f? Do you understand that it is a derivative? Do you know what the gradient of f is? Kind of lives in the xy plane, right? It's a projection. Sorry, I kind of jumped back to. Your gradient of f is a vector of the partials. And that your gradient of f dotted with, right, the tangent vector, but the projection of the tangent vector down there, right, on the xy plane is going to be u, right, always perpendicular. All right, hope that made a little bit of sense. I know it's a lot of material, and practice some, and I will see you in our live session.